So the first claim in the proof of the lemma goes as follows. So they claim that there exist these coefficients that which they notate as Cij. So these coefficients that depend on these indexing sets Ij, which are subsets, I and j are subsets of the natural numbers up to n. And they're in the field f, since the polynomial p is a polynomial over the field f. So they claim that there exist these coefficients such that the following equality holds. That if we evaluate the polynomial p at the difference between the vectors x and y, that it equals the sum over all I, j, these indexing sets that are subsets of the natural numbers up to n, such that I and j are disjoint, and the cardinalities of I and j sum up to a number no greater than d, then they claim that this polynomial evaluated at the difference of these two vectors is the sum over all I and j that are subsets of the natural numbers up to n that satisfy these conditions, where we're summing over Cij times x raised to the I. Recall our notation from our previous video, how this notation is defined. X raised to the I, the set I, and y raised to the set j. And it might seem strange why they're writing it like this, but once we play around with a few toy examples, this claim becomes, you start to see that it is actually a natural claim to make. So let's consider the following toy example. So again, we're going to let n equal 2 and d equal 2. And let's consider the polynomial, or also remember our field is the real numbers r. And let's just consider the polynomial p equal to 2 times x1 times x2. Remember, since n is equal to 2, our polynomial is a polynomial in invariables. So p, we can think of p as polynomial in invariables, and it's equal to the product of 2 with x1 and x2. So check this out. We can write the polynomial evaluated. Let's consider two vectors a and b. So a is equal to a1 comma a2, and b is equal to vectors, some vector b1 comma b2. So b is a vector with components b1 and b2. So if we evaluate the polynomial at the difference, so this polynomial p at the difference between a and b, then we're going to get the following. We're going to get 2 times, well, notice let me write it like this. We're going to evaluate this polynomial at a1 minus b1 at the vector a1 minus b1 with a vector whose first component is a1 minus b1 and whose second component is a2 minus b2. So this is the same thing as saying we're going to evaluate this polynomial at a1 minus b1, and that we're going to substitute a1 minus b1 for everywhere we see an x1, and we're going to substitute a2 minus b2 everywhere we see an x2. And so this gives us 2 times a1 minus b1 times a2 minus b2, and if we sort of expand this out, this gives us 2 times a1 a2 minus a1 b2 minus 2 a1 b2 minus 2 b1 a2 plus 2 b1 b2. And look at this lemma sort of starts to make sense because I can rewrite using this notation that they made to sort of reduce the number of indices that we're writing, sort of, and make things a little bit cleaner. We can rewrite this using our notation. So this is, recall that the vector x raised to, say, the power 1, for example, the singleton 1 is equal to just a1. So we can rewrite this this sum of, or this expansion in the following way. We can rewrite it as 2 times the vector a raised to the 1, 2 power minus 2 times the vector a raised to the 1 power times the vector b raised to the 2 power minus 2 times the vector b raised to the 1 power, the singleton 1 rather, times the vector a raised to the singleton 2, plus 2 times the vector b raised to the singleton, or rather not the singleton, to the set 1, 2. So using our new notation, we can sort of rewrite this in the form of this notation, and this claim starts to sort of squeeze out of this toy example here. And we can go further and say that this is equal to 2 times a raised to the 1, 2 power, the set 1, 2, times b raised to the empty set, because b, any vector, based on how this notation is defined, any vector raised to the empty set is just equal to 1. So this is equal to minus 2a raised to the 1 power, b raised to the singleton 2, rather the singleton 1, a raised to the singleton 1, minus 2 times b raised to the singleton 1 power, times a raised to the singleton 2 power, plus 2 times the vector b raised to the set 1, 2, times a raised to the empty set. And you can sort of see now, we can sort of see that indeed we are summing over all subsets ij that are subsets of the positive integers, in our case, in our toy example, of all positive integers up to 2. And notice that each of these exponents is disjoint. So if I raise a to something, then whatever I raise b to, if it's the same term, then we're raising b to an exponent that's disjoint from the exponent that we're raising a to. And so, and notice moreover that if we add the cardinalities of these two, of any term, if we add the cardinalities of the exponent of a plus the exponent of b for any term, then that sum is going to be less than or equal to d. Remember, d in our case is 2. And so, yeah, it does seem like a natural claim to make that this thing is true. And you can try out the case when n is equal to 3, n equals 3, d equals 3, and you can check out the polynomial just x1 times x2 times x3. And you really start to see why this how this claim was extracted from sort of playing around with examples like this.